There's a stretch of highway in Virginia where drivers cross 17 miles of open water, and for 2 of those miles, they completely vanish. Not into fog or beneath an overpass, but under the Chesapeake Bay itself. The road does not arch over the shipping lanes, it dives beneath them, buried 50 feet below where aircraft carriers pass overhead. This was not a choice made for convenience or cost. The United States Navy demanded it. For more than 3 centuries, the Chesapeake Bay carved Virginia into 2 separate worlds. The eastern shore sat visible across the water from Norfolk, close enough to see on a clear day, but separated by the unpredictable mouth of the bay. Wind decided when people moved. Tide dictated schedules. Fog erased the crossing entirely some mornings. Before automobiles arrived, this isolation felt manageable. Inconvenient, sure, but manageable. Then cars appeared, and the problem compounded. By the early 20th century, ferries became the only connection. They hauled people, produce, livestock, and eventually vehicles across water that never guaranteed safe passage. An hour on a calm day. No service when storms rolled in. That uncertainty shaped every decision. Farmers watched crops sit waiting for transport. Freight companies planned around weather windows. By the 1950s, traffic had overwhelmed the ferry system completely. Lines stretched for miles. Trucks idled for hours. Every season brought delays that stacked higher than the year before. Everyone agreed something permanent needed to exist. The question was not whether to build it. The question was how to build it in water that connects directly to the Atlantic Ocean, where forces far larger than traffic flow through every day. Building a bridge seemed obvious at first. By the 1950s, suspension bridges were getting longer, reaching farther, conquering rivers and bays across the country. On paper, a bridge across the Chesapeake looked straightforward, except one detail changed everything. The mouth of the Chesapeake Bay serves as the front entrance to Naval Station Norfolk, the largest naval base on the planet. Every aircraft carrier, every destroyer, every supply vessel assigned to the Atlantic Fleet must pass through a narrow corridor called Thimble Shoal Channel to reach open ocean. During the Cold War, that passage carried strategic weight. Navy planners raised a scenario engineers could not dismiss. What happens if a bridge collapses into the channel? It did not matter whether it was an accident, a storm, or an attack. The wreckage blocks the passage. The fleet gets trapped inside or locked out when it needs to return. They called it the cork in the bottle problem, and the Navy made their position unmistakable. Nothing could stand above those shipping lanes. Nothing. That single requirement eliminated the simplest solution and forced engineers to rethink the entire approach. They could not cross over the critical channels. They had to disappear beneath them. The solution became a hybrid system. Instead of one continuous structure, they proposed a chain of different components, each solving a specific challenge. Low trestles would span shallow sections where ship traffic was minimal. High bridges would arch over secondary channels where collapse would not trap the fleet. But under Thimble Shoal Channel and Chesapeake Channel, the roadway would sink completely out of sight. Elegant on paper, nightmarish in practice. Making those tunnels work required solving an impossible problem first. Where do you put the tunnel entrance when there is no land? Just open water, soft seabed, and currents that never stop moving. If the road needed to dive underground, it required solid ground to do it from. That meant creating land where none existed. The answer was 4 artificial islands positioned precisely at each tunnel entrance. These islands would anchor everything, housing ventilation systems, emergency access, and the transition points where bridge became tunnel. But building islands in 30 feet of water exposed to Atlantic weather, that is where things got interesting. Construction started by placing rock dikes on the seafloor to outline each island's shape. Inside those boundaries, hydraulic dredges pumped millions of cubic yards of sand into position. What rose from the water was not solid ground initially. It was a temporary landscape that needed to settle and compress under its own weight before anything permanent could be added. The islands were intentionally built taller than their final height, allowing soft sediments below to squeeze down before real construction began. Only after that settling slowed could work continue. To keep waves from washing the sand cores away, crews armored each island with massive stone layers. Small filter rocks came first, then granite blocks weighing several tons each. This armor reached above and below the waterline, protecting against wave action, tides, and storm surge. For a period, it must have looked surreal. Land appearing in open ocean where only water had existed before. The tunnels themselves were not carved through bedrock. They were built hundreds of miles away. Engineers chose a prefabrication approach, treating each tunnel section like a massive floating vessel. The sections were constructed at shipyards in Texas as sealed steel shells designed to float. Each completed section was launched into the water and towed 2,000 miles up the Gulf Coast and along the Atlantic to Virginia. Losing one at sea would have delayed everything by months. While those tubes traveled, another operation was happening underwater. Crews dredged trenches across the bottom of each shipping channel, preparing foundations with extreme precision. A layer of pea gravel was placed and leveled to within inches using specialized equipment dragged along the seabed. If that foundation sat uneven, the rigid tunnel sections could crack or fail once buried under sand and pressure. When the time came, each floating tube was positioned over its trench and slowly lowered into place. Divers worked underwater, while support crews coordinated from above. Once two sections met, they were sealed from outside using concrete poured through tremie pipes. After curing, the water trapped between sections was pumped out, and workers entered to weld the steel shells together from inside. What happened next determined whether this entire approach would work. Concrete lining followed, transforming those floating steel shells into permanent roadways beneath the bay. Section by section, the tunnels took shape. Each connection required absolute precision underwater. Divers sealed joints with concrete poured through tremie pipes, while support teams coordinated from the surface. After each seal cured, water trapped between bulkheads was pumped out, and workers entered to weld steel shells together from inside. It was a process that demanded unwavering focus. One mistake could compromise an entire section. Meanwhile, above water, the bulk of the crossing was advancing at remarkable speed. Most of the Chesapeake Bay Bridge-Tunnel consists of low-level trestles stretching across shallow sections. These spans needed to be built quickly and consistently. The seabed offered no bedrock for anchoring, just sand, silt, and clay, layered thousands of feet deep. Every support pile depended entirely on friction. Massive pre-stressed concrete cylinders were driven deep into sediment, some reaching over 170 feet below the waterline. Once positioned, those piles gripped surrounding soil tightly enough to support roadway weight, traffic loads, and storm forces for generations. Efficiency demanded specialized equipment. The construction crews relied on a jack-up pile-driving platform known as Big D. This machine transformed open ocean into a stable worksite. Steel legs descended into the seabed, then the platform jacked itself above the waves. Elevated and steady, cranes and hammers operated with precision no floating barge could match. Construction progressed like clockwork. Piles positioned, jetted into sand, driven to depth. Trestles advanced steadily across the bay. But this efficiency created vulnerability. The entire operation depended on keeping Big D operational. There was no backup equipment of equal capability. By early 1962, the project was moving forward on an unforgiving timeline. Then the ocean intervened. A nor'easter stalled off the Atlantic coast. Instead of striking and moving on, it remained stationary. Wind and surge hammered the mouth of Chesapeake Bay relentlessly. Big D was jacked up to ride out the storm, but waves began pounding the underside of the elevated deck. Each impact transmitted force downward through the steel legs. The structure endured blow after blow until it could not anymore. The legs buckled and Big D collapsed into the sea. As the storm continued battering the construction site, crews were evacuated by helicopter under dangerous conditions. No lives were lost in the collapse, but damage extended beyond the sunken platform. Across the project, partially armored island sections had eroded. Sand washed away where protective rock had not been placed yet. The storm exposed every weakness in incomplete defenses. Yet something crucial became clear in the aftermath. Concrete piles, already driven, held firm. Tunnel sections beneath the seabed did not shift. The storm had tested everything under real conditions, and the core design survived. From that moment forward, crews left nothing partially protected. It was a lesson learned at considerable cost. Construction resumed with renewed caution. The schedule had been pushed back nearly 3.5 months, but by spring of 1964, the crossing was ready. On April 15th, the Chesapeake Bay Bridge-Tunnel opened to traffic. For the first time in Virginia's history, the eastern shore connected to the mainland by fixed roadway. Ferries that had defined life along the bay for generations were no longer the only option. Drivers could cross on their own schedule. The experience was unlike anything motorists had known. Roads stretching across open water, diving beneath the bay through tunnels, rising again onto man-made islands. But once novelty faded, operational realities emerged. The original facility was 2 lanes only, one northbound and one southbound. There was no physical separation between opposing traffic. Many sections had no shoulders and no escape routes. Once vehicles committed to the crossing, there was no turning back. Any incident, regardless of size, could shut down the entire structure. The Chesapeake Bay Bridge-Tunnel was undeniably a triumph. It worked exactly as designed, but it operated near its limits from day one. By the late 1980s, traffic volumes had grown steadily for decades. The 2-lane configuration had become a serious liability. Engineers proposed building parallel trestles alongside the original structure. Northbound and southbound traffic would finally separate, reducing collision risks and increasing capacity across much of the bay. Construction began in the mid-90s. New trestles rose just feet away from existing spans while traffic continued flowing. It was delicate work carried out in open water. When parallel trestles opened in 1999, improvement was immediate. But expansion remained incomplete. At the tunnels, the crossing narrowed again. 4 lanes forced into 2, recreating bottlenecks that had plagued the facility before. The tunnels became the weakest link. Solving that bottleneck meant returning to the most challenging part of the entire crossing. The original tunnels used immersed tube construction, appropriate for 1960s technology and standards. Repeating that approach decades later created complications. Dredging trenches across active shipping channels would disrupt maritime traffic and disturb massive sediment volumes on the bay floor. Engineering had advanced. Expectations had changed. Instead of trenching, engineers chose to bore a new tunnel beneath both channels using a tunnel boring machine. Ships could pass freely overhead while construction continued below. The seabed remained largely undisturbed. The machine was massive, purpose-built for extreme pressure. It functioned as a moving factory, cutting through saturated soil and installing concrete segments behind itself, one ring at a time. Even superior technology encounters obstacles. Partway through, the machine struck something unexpected. A ship's anchor buried in sediment, lost decades earlier, never recorded on any chart. Impact damaged the cutting tool and halted progress entirely. Recovery required stabilizing ground ahead of the machine and entering the cutter head under hyperbaric conditions. Slow, hazardous work that delayed the project nearly a year. In January 2025, the machine finally broke through into the receiving island. The most difficult phase was complete. What remains is a structure that was never meant to be static. Every decision was shaped by what the bay permitted and what it forbade. 17.5 miles of bridges, trestles, tunnels, and artificial islands were assembled in open water with inch-level tolerances and consequences measured in lives. The Chesapeake Bay Bridge-Tunnel connects two shores across open water, above it and below it, making an impossible crossing feel routine. 7 men lost their lives building the original span. Over 2,000 workers labored in rough water underwater on shifting sand. The structure they left behind is not one continuous bridge. It is 6 separate systems working as one. 2 high-level steel bridges lift traffic over secondary channels. 2 tunnels are roughly a mile each. 12.5 miles of low-level trestles consist of 858 individual concrete spans. 2,600 pre-stressed concrete piles were driven over 170 feet deep into the seabed, where bedrock sits thousands of feet below. 4 artificial islands were built from 4 million cubic yards of sand, protected by 1.2 million tons of rock armor. Some boulders weigh 4 tons individually. The original tunnel tubes were not bored. They were immersed, 74 steel sections in total, each roughly 300 feet long, were built in Texas and towed 2,000 miles to Virginia. They were lowered onto gravel beds, leveled to within 1.2 inches underwater. When Big D sank in 1962, it was valued at $1.5 million. Rebuilding it today would cost between $20 million and $40 million depending on the manufacturer. Not 1 cent of federal, state, or local tax money funded this project. Not the original construction. Not the parallel trestles. Not the new tunnel bore currently underway. Everything was financed through bonds and repaid by tolls collected from those who use it. What mid-century engineering accomplished here remains difficult by modern standards. The Chesapeake Bay Bridge-Tunnel solved a problem at extreme scale, creating a fixed crossing where the Navy said bridges could not stand, and geography said tunnels could not exist. It connects 2 shores across water that refuse to cooperate, making 17 miles of impossible infrastructure feel ordinary every time someone drives across it.